All right, guys, we are going to cover objective 2 in this video, which is going to be focused on ground state and excited state of electrons. So we're going to talk about what each of those are. We're going to talk about how electrons can move between the two, and then also what a bright line spectrum is. So just to review from our first objective, just remember that we talked about how electrons are around the nucleus in that empty space and that they're in distinct energy levels. Okay, so that first energy level, which is closest to the nucleus, has that lowest energy. And then as those electrons have more energy, they can exist farther from that nucleus. So just remember that that positive nucleus and those negative electrons would naturally attract each other. So in order for those electrons to stay away from that nucleus, they need to have more energy. Okay, and the further away they can get, that's the more energy that they're going to have. So with that said, when we talk about electrons absorbing energy, think about when they absorb energy, they're going to move up higher. Okay, they can be farther from the nucleus. And then as they release energy, they're going to go back towards the nucleus. So if you can understand this concept, it helps this ground state, excited state be a little bit more clear. All right, so let's talk about ground state first with this. So with our ground state, this is where the electrons in an atom are occupying the lowest energy configuration possible. So basically they're filling up the first and they're filling up the second. The third energy level gets a little bit trickier that we'll talk about later on. But it's the idea that they're in that lowest configuration possible. This is the one configuration that's found on the periodic table. So if it's the configuration that you see on that periodic table, then you know it's the ground state. So for like sodium, if for sodium I have 281, that's its ground configuration. Anything else for sodium is going to most likely be an excited state if we're talking about an atom. So an electron absorbs a specific amount of energy, and this is the difference between the lower and a higher energy level. It is able to jump up to that outer energy level, and it creates this excited state. So that electron here, which has a certain amount of energy to begin with, it has to absorb a specific amount, which allows it to directly move up to that, in this case, second energy level. And now we say that this atom is in the excited state because that electron is in a higher energy level than it should from absorbing energy. Okay, but that's an incredibly unstable state to be in, this excited state. So the excited state is where they're occupying these higher energy configurations than they normally would. This is the configuration that would not be on the periodic table. So let's talk about how do we just identify an excited state. So if we look at neon on the periodic table here, we get the configuration 2-8. So this configuration here matches the periodic table. I'm just going to abbreviate periodic table as BT here. Okay, so this configuration has to be the ground state. Okay, if I have neon, but I have the configuration 281, now I still have the same total. Okay, so same total, we haven't lost or gained. Okay, but now I can see that this one electron that was in the second energy level is now up in the third. That means that it moved up to a higher energy level. So this must represent this configuration, an excited state. Okay. So when it's in that excited state, that excited electron, that one that has more energy than it normally would, is going to release a specific amount of energy, the difference between a higher and a lower energy level, and it's going to fall down to a closer, lower energy level. Okay, if it releases enough energy, it will return back to its original ground state. So in this little diagram here is just showing it's returning to a lower energy level, and then you're going to see the emission of energy being given off by it. Okay, so one little way to summarize this right now is if it goes from the ground to excited state. So again, we're talking about like we have the first, the second, the third, the fourth PEL. Remember, this is the lowest energy and the highest. So if it's going from a lower to a higher, okay, it has to absorb energy. So ground state to excited state is the absorption of energy to move farther away from the nucleus. Okay, the energy moves higher. If we talk about the excited state to the ground state, this is when the electron falls to a lower energy level. It goes closer to the nucleus. So when it does that, it's got to get to a lower energy state. So it's got to release that extra energy that it had when it was the excited state. Okay. All right, one other little piece of this is just let's review quickly. How do we tell if it's an excited state or a ground state? How would you write a possible excited state? You'll see questions on that. So the big thing is these are on the periodic table. These are the only ground states. When I do this, again, I have to have the same total. Okay, and I'm going to move electrons higher. Okay, and I'm going to give you one scenario which wouldn't work that sometimes students will do. So with this one, I still have to have 13 electrons when I come over here. So one good one might be a 2, 7, 4 configuration. I've just moved one from the second up to the third. Or maybe I'll have 2, 8, 2, 1. I've moved one from the third up to the fourth. Now, the one thing you can't do is you can't overfill the second energy level. This is the maximum number that the second energy level can hold for second PEL. So I can't do 1, 9, 3. Right? That wouldn't work. So just be careful with that second energy level. For boron, I could have something like 1-4. I've moved one up. Again, still keeping the same total. Or I could have 2, 2, 1. I've moved one up to the third. Still 5 electrons. Okay, for potassium here, I could have something like 2, 8. I want to make that 7. 7, 2. Or maybe I could even have something like 2, 8, 8, 0, 1, where I move that one electron up to the fifth energy level. So again, all these are possible. The third energy level can go up to 18 electrons, so I could move one up to the third energy level in this case, but second is full, so I can't do that there. Okay, so you want to be able to talk about ground state and excited state, and then also be able to come up with different configurations that apply to the ground state, which is your periodic table configurations, and then those excited states. So one way that we know that this is occurring has to do with bright line spectrums. So elements produce bright line spectrums, or they emit colors of light or wavelengths of light based on this movement of their electrons. So these spectrums get produced, or the color of light, like in a neon lamp, is produced when an excited electron falls from a higher principal energy level to a lower one and releases light energy. So those colors are being released because that excited electron's falling from that higher and lower. So from like an excited state to a lower energy level, and releases light energy. So this is definitely important, this definition, especially in terms of a short response question. So each different drop in energy levels gives off light with different amounts of energy and then gives a different wavelength. So these colored bright lines are different from element to element. It makes each spectrum unique to that particular element. It's basically like a fingerprint for that element, and it's constant no matter what isotope it is. So we can identify elements in a mixture by comparing the bright line spectrums of specific elements to the mixture. So let's look at some examples. It wants us to tell what is in spectra A and B. So if I look at A and I see these two lines here, and I look at sodium and it has those two lines, there's no other lines in sodium. So as long as the mixture has both of these lines, which it does, then I know that sodium is in mixture A. Okay, if I look at lithium, I see that this line and this line both line up with lithium. Lithium doesn't have any other lines, so as long as it has every line in it possible, which it does in this case, lithium must be in that mixture. Okay, and then I don't see enough of these lines. Like you might see that like, oh, maybe this line from helium is in there, but this one isn't. And as soon as there is a line that's not there, it can't be in the mixture. If I look at B here, I will see that hydrogen, okay, these two lines, and every single line of that element has to be in the mixture is there. So this would have hydrogen. And it looks like based on those two lines that I also have the two lines that were in lithium. So that also has lithium. Okay, with helium, this line here is not in either of them. If you look down here, so that means helium isn't in either of those mixtures. Okay, so that's all you really need to cover in this set of notes for today, and we'll be moving on to different activities.